Hi everyone! In this episode, I'll show you how to implement streaming in your chat applications using OpenAI. You might be wondering why streaming is necessary. Well, streaming significantly improves user experience because it allows users to start receiving messages early. It creates an interactive, almost animated feel on your platform and helps avoid uncomfortable pauses during user interaction. OpenAI provides settings that enable us to implement this feature, so we will explore how to use them today. However, integrating streaming isn't without its challenges. For one, you'll need to set up a WebSocket server that connects with OpenAI to handle user queries and stream responses back to the front end. Additionally, we will have to manage increased component re-rendering, as streaming means we receive messages piece by piece rather than all at once. In this video, we will see how state management tools like Redux and memoization hooks from React help optimize this process, ultimately achieving a setup where message streaming is smooth and minimized unnecessary re-renders. In the previous video, we created a foundation for our chat and messages. In this video, we will look at the updated code that, instead of echoing messages, implements communication with the OpenAI. You will find all links to the previous video and the code from the previous and this video in the description. Now we are ready. Let's get started. Okay, here is our WebSocket server, which needs to be set up on a separate port if you also have an HTTP server as in my example. In this case, we will specify port 3001. We create a new instance of the WebSocket server that listens for incoming connections on the specified port. The WebSocket server triggers a connection event every time a new client connects, and the callback function receives an argument WS, which is a WebSocket connection object with the client. Inside the connection handler, a message about the new client connection is displayed. This event handler for the specific connection, WS, triggers every time the server receives a message from the client. The message data is presented as a JSON string. Inside the function, there is an attempt to parse the JSON string to get a message object. If the parsing is successful and the message is correctly formatted, the fetch text OpenAI function is called, which interacts with the OpenAI API to fetch a response. If there is an error parsing the JSON or any other during message processing, an appropriate error message is displayed. To perform fetch text OpenAI on this server, we need to establish a connection with OpenAI, and for this we create a client. We can also see on the API documentation website the main elements of the code we need. We define our model, the message we send, and set the true flag for streaming. Our function is asynchronous and doesn't interfere with execution of the rest of the code on the platform. Inside the asynchronous function, we wait for the response and also process each piece of data that comes in. We also check if there is data inside the response received from OpenAI and send data to the front end in JSON format. There are three types of messages sent to the front, signaling the start, process, and end of streaming. We can organize this in a way that suits you. I have done this so that I can signal the application that recording has started, is ongoing, and has ended. It might be convenient to then disable buttons or otherwise manage states in the application. We also assign a unique ID to our message, but we will return to the structure of message later. Now let's see how we receive a message on the front end and how we handle it, tracing its path. We will start by noting that our application now includes react-redux, a popular library that manages the state of our components. Redux is a powerful state management tool that centralizes application state into a single immutable state tree, making state management predictable and efficient, especially useful in large or complex applications with many moving parts. Redux is based on the FLUSK architecture, developed by Facebook, which introduces a unidirectional data flow. This design simplifies how data is handled across the application by enforcing a single flow of data, which makes the logic more predictable and easy to understand. In a FLUSK architecture, there are three major parts. Actions. These are payloads of information that send data from your application to the store. Dispatcher receives actions and broadcasts them to appropriate handlers. And stores hold the state of your application and change it in response to actions received from the dispatcher. Here is how we've implemented this in our application. First, we set up our Redux Store. Here, Configure Store from Redux Toolkit helps us define our store, linking it with the message reducer, which handles all operations related to messages. This is the central point where our application state is managed. Next, we address the initial state setup and interaction through reducers. This code segment showcases the Redux slice that manages messages. It begins with retrieving any existing messages from local storage, demonstrating Redux's ability to handle initial state based on past interactions. The reducers provide functions for updating the state based on actions such as adding new messages or setting all messages. The function save messages uses Redux Toolkit's createAsyncThunk to handle asynchronous operations like saving the current state of messages back to local storage. This ensures that the application state is maintained across sessions, aiding in a seamless user experience. By utilizing Redux and the Redux Toolkit in our application, we align with the streamlined version of FLUSK architecture, simplifying state management and ensuring that all parts of our application can efficiently manage and track state changes. Okay, now that we've set up our Redux Store, let's explore how the story is passed down to our components and how we interact with it. In React applications, this is achieved through the use of the provider component from the react-redux library. The provider wraps the entire application and allows every component within our app to access the Redux Store if needed. Here is how we integrate the Redux Store into our React application. So let's delve into our chat component to see how it interacts with the Redux Store and the WebSocket server, ensuring real-time message management. First, we use useSelector to retrieve the current state of messages from the Redux Store. We optimize performance by using shallow equal to prevent unnecessary renders. This function ensures that component actually updates when the messages array actually changes. UseDispatch gives us the ability to dispatch actions directly to the Redux Store. So our application is well equipped to create a stream of messages. We have a list of messages, a dispatcher for sending actions, and WebSocket connection managed with useref. This useref hook is crucial as it maintains a persistent reference to our WebSocket connection across multiple renders because we need it at various points within the component. We utilize useEffect because it connects to an external resource, our server. This effect handles the setup and teardown of the WebSocket connection, ensuring that it persists across component renders. The WebSocket connection functions include connecting to the server, handling message exchanges, and disconnecting. Upon component unmounting, the same connection is returned, which helps in maintaining it across renders. This function processes incoming WebSocket messages and dispatches actions to add or update messages in the Redux Store. It ensures all messages from the WebSocket are reflected in the app's UI in real time. For instance, the first message triggers the creation of a new item in the list, while subsequent messages update an existing item. It's important to note that Redux inherently maintains the principle of immutability within React with the Immer library. While developers can write code as if they were mutating objects, Redux ensures that the actual state in React remains immutable. In our message list component, we use keys to help React identify specific messages that need updates. We also optimize all functions based as props with useCallback hook and components with useMemo hook to minimize re-renders even during continuous streaming. And an interesting aspect of our setup involves interaction with local storage. As previously mentioned, this use effect triggers the save messages thunk to persist messages to local storage whenever the message's array changes, ensuring all messages are saved asynchronously and the state is maintained across sessions. Another noteworthy point is our application's hashtag addition feature above the input box. For frequently changing and minor state like this, it's not always practical to use a heavy solution like Redux. In the header, we don't always need the input state, and using Redux where you must subscribe to a component using QSelector could lead to constant re-renders if the state changes frequently. Therefore, we use useref to access the input value directly. So we still pass props. This significantly reduces the number of re-renders in our case. So this trick at the end helps us minimize possible re-renders. So this overview should enable you to build a streaming chat application that operates smoothly without unnecessary re-renders. And I want to say thank you for watching, and until next time, goodbye.